my name is Ronit Avadhuta, and today I'll be teaching you guys about the rotational equivalent to a lot of the kinematic equations that you might have heard of or seen before. So let's just start out with the basic four kinematic equations. So one of them is that the final velocity is going to equal the initial velocity, so F stands for final, I stands for initial, plus the acceleration multiplied by the time. And this really gets at the key of like what is acceleration. To get acceleration, you're essentially dividing the change in velocity over the change in time. And this is really taking advantage of that definition to get that final velocity. That's one of the equations we have. And another one of the equations we have is if we take the change in x or displacement, and we're going to take this displacement and we're going to say that this is going to be times 1/2 times the acceleration times squared. And we're going to add this to the initial velocity times time. And that's very helpful because you can usually, what we can do is we can usually turn this into x equals 1/2 times a times t squared plus vi times t for initial velocity plus, and then we can put the initial displacement. And this really takes advantage of like, okay, what is the definition of displacement? Displacement is going to be very closely related to velocity times time. And we have those two. And just to clarify that this is basically just a rearrangement of this. The third one we have is that change in x can also be represented as really the average. So that's going to be if we have our initial and our final divided by 2 and then multiplied by time. So it's just average velocity times time, which is that definition we were getting at earlier. So a lot of physics is really just taking advantage of the definitions we already know. Now, what we're going to have is also very cool and important one, especially that doesn't involve time. All the ones you've seen so far has involved time. This one does not involve time. We're going to say that the final velocity is going to equal to the initial velocity squared plus 2 times the acceleration. And this is going to be multiplied by the change in x. So this one's a little bit less clear where it comes from, but you can see that pretty quickly. It comes from, I mean, just a decent amount of calculus just applying on the basic definitions we have. So these are the basic 4 kinematic equations you should have covered so far. But today I want to talk about the rotational equivalence. Now, to understand that, we have to look at some new variables. We're going to realize that our change displacement is not really going to be a distance, but it's probably going to be an angle. And we're really going to like radians. So we're going to work in radians. And the reason is I'll get to that later, but we're just going to work in radians. So our x becomes a theta. Then what happens with time? What does time become? Well, in a rotational motion or rotational world, time is still time. Okay, what's our acceleration going to be? Can we keep that the same? Acceleration is still acceleration. Well, it's going to be a little bit different. It's going to be not in the same units. It's going to be radians per second square, not really necessarily meters per second square. Just like how for x we'd have meters, but now we'd have radians. So then we're going to represent this with alpha. Likewise, we're going to represent, how do we represent velocity? It's radians per second now. So this was radians per second squared. And velocity, I'm going to represent it with a W because that looks very similar to the Greek letter omega, which is used for this symbol. And we're going to say that it's radians divided by seconds, just by definition. We can walk to see, find out how many radians can we go in a given amount of time. It's going to be omega. Okay, so this is pretty cool. Like, what can we do with this? Well, let's take a look here. If we really apply these same sort of concepts to what we had before, let's take the first equation. We have that the final rotational velocity is going to equal to the initial rotational velocity plus alpha, which I'll just use an A, and times the change in time. And boom, right here we have an equation for really just the basic definition, but just turned into the rotational world. Likewise, you have the change in theta is going to be 1/2 alpha times time squared. That's not going to change too much. We're going to have initial rotational speed times time, and then we're going to have the initial change in theta. That's second one. Next one, we have change in theta is equal to average angular speed, which you can do very similar to how we did before up over here. And we're just going to multiply by change in time. Lastly, we have the final angular speed is equal to the initial angular speed plus 2 times the alpha, which is our angular acceleration, times our change in theta. And those are the rotational equivalents. Now, I'll just give you a second here to write this stuff down, really just take it in and realize that we're just using the definitions to describe really a lot of things. Okay, good. Now let's look at maybe some more interesting things. So let's say you're given acceleration as a function of displacement. So if you are given acceleration as a function of displacement, do not fret, you can still do things with it. The question is how? Well, first we have to realize that we have to go back to our definitions. As I mentioned earlier, acceleration is really just the change in velocity over time. But it's not really accurate to just say v over t, because that doesn't really say the change part. That just takes, okay, what's the velocity? We could have started at a velocity of 10. We don't really know. So to represent that, I'm going to use a d for just both the change in time and both the change in velocity. Now, when we do this, there's some really cool things that we can play around with, especially in the calculus world, because what we can do is we can multiply by 1. Now, that might not sound too super interesting, but until you realize that dx over dx is 1. And yeah, this works out because it's the same numerator, same denominator. What we can now do is we can swap the denominators because it's multiplication, right? And we can say that acceleration dv or dx times dx over dt. Now, you should instantly realize that this dx over dt part, okay, that part is just going to be velocity. Because just like how I said acceleration is the change in velocity divided by the change in time, velocity is just the change in x divided by the change in time. Time is really what we use to get to different dimensions, in a way. So this is going to be velocity, and then we're going to have dv over dx. And this is multiplication, so ordered, it's commutative. Then what we can do is multiply both sides by dx. We get a dx equals v dv. So notice how, in order for this to work, we now need acceleration as a function of displacement, which originally we were given. So that's really interesting. And this v over dv, if you don't realize what that might be right away, you might want to replace it. Just think about it as taking the integral of x with respect to x. What you're eventually going to get is you're going to have integral of the left-hand side, the a over x dx, which we are yet to know depends on the function. And this is going to be equal to v squared over 2. Because we have to raise that 1 to the power 2 and then divide by 2. And this is our final equation we have here. Likewise, I'm going to do the same thing now, but in the rotational world. So if we do alpha, we can say that's the change in omega over the change in time. Alpha, I'm just going to represent with A now. Don't confuse it with the tangential. We're working rotationally now. We can multiply it by the change in theta over change in theta. And if we swap them, we get that, okay, we have now the change in theta over change in time, which is basically how we define our omega. And once again, we're left with this sort of idea, and we can just move it to this side, take the integral. So you have integral of alpha of theta now, because it's d theta. And this is all going to be equal to well, w omega with respect to omega is just going to be this again. So now we have both rotational and acceleration version. Now, this is great and all, but what if we have a different predicament? Let's say we have velocity as a function of displacement. Yeah, and usually we get stuff in terms of t, but if we can express it in terms of x, we can do some cool stuff with it. So what we can do is we can look at, okay, what is the velocity? So looking at what is velocity, we can say, okay, velocity should just be change in x over change in t. Okay, not bad, not bad. And let's see, what can we do here, right? Let's try multiplying by, how about we multiply, I don't want to multiply by, what should you say here? I don't want to multiply by anything that's gonna cause too many problems. I want to say that we are given v as a function of x. So what we can do is honestly simpler than what we did before. If we just divide both sides by v of x, so you have v of x dx divided by dt. But if we then multiply both sides by dt, we have integral of 1 dt is equal to integral of v x dx, which is what we were looking for. And notice how this integral of 1 dt is just going to give us the change in time. It's going to go to the integral of, sorry, my bad, because remember we have to take reciprocal. It's going to be 1 over vx. And just to make that a little bit more clear when we're doing it this time, let's try looking at it with omega as a function of theta. What we're going to do is we're going to say, okay, we're going to define it, of course, like this. So we're going to divide both sides by this w, and we get 1 over w times d theta dt. And remember that this omega is still a function of theta. Putting it over to this side, then we get that we have 1 dt is equal to the omega of theta d theta. Taking integral both sides, we have change in time is also equal to 1 over d theta, and with respect to theta. And these are some just cool calculus formulas that you can apply to some of the stuff I showed you today. Thank you for watching, and I hope you learned something. Bye, guys.